Good evening. We have a few more people coming in. I see there's some seats in various places around, and I invite you to be seated. I'm Dick Meserve. I'm the president of the Carnegie Institution, and I'd like to welcome you all to a special event we're having this evening, which surrounds the publication of a book entitled First Contact. And this is a remarkably exciting time in science in many areas, but the subject we're going to discuss tonight involves the convergence of two areas where there really has been remarkable learning over the last several years. First is the sort of general area of astrobiology, which is the trying to undertake the scientific understanding of the origins of life, how it was that it came about. It's obviously a hugely profound question in many dimensions. And it's one in which there's a lot of Carnegie scientists who happen to work in that area. And the second is the development of an understanding about extrasolar planets and the discovery of them. And the now, I think, inevitability that we will find planets that have properties that are appropriate and suitable for the development of life elsewhere in the universe. So we have sort of two different strands of science in different areas that are converging to make this really quite a remarkable period. And we're going to hear first tonight from Mark Kaufman, who is a science reporter for the Washington Post. And as I mentioned, he is the author of the book First Contact, which has just been published, and it explores this exciting area of science. And then secondly, we're going to hear from Paul Butler, who is a Carnegie scientist, who is responsible for finding about half of the 600 planets that have been discovered orbiting nearby stars. And he's going to talk a little bit about how he goes about doing that. And so I'm not going to stay up here longer because we have two exciting speakers. So let me turn this over to Mark Kaufman.
Hello, everybody. First off, I'd just like to say it's a huge thrill and honor to be here. As a journalist, I've been in the audience a number of times listening to people speak, and just as a citizen of the area, I've been here as well, listening to speakers. So it just feels so wonderful to be able to have information to impart to you folks as well. And I am indeed going to speak for a while, and then I will introduce Paul, who will speak for a while, and then he and I will sit together, and I will ask him some questions, and then we'll take questions from the floor as well. Just as a start, the book that I wrote is primarily about the issue of life beyond Earth. Astrobiology is a two-headed beast in that it is both how life began on Earth, but it's and then also what is there out there beyond, and that's the part that I focused on, and that's the part, or one of the parts, that is incredibly dynamic now in terms of what kind of science is being done. We live in an extraordinary time, and extraordinary breakthroughs are coming every day, or almost every day, and a lot more is on the way. So. When you think about it, human beings have kind of, for as long as we know, people have thought at all and written things, they have sensed that there is something out there. They have wanted there to be something out there. There are gods, angels, in the Islamic tradition, jinns, heaven, it's all up in the sky. So you could look at it as either kind of an intuitive sense that there is something there, or a hope that something is there, and that we're, in that sense, not alone in the universe. But until very, very recently, this was all based on belief, or to some extent, rational deduction, but there was no data. There was no real science until very recently. And that resulted in some very unfortunate things. Giordano Bruno, who is kind of the patron saint of astrobiology, this is a statue of him at the Campo de Fiori in Rome, about a half a mile from the Vatican. Alas, in the year 1600, he was put to death at the stake right at this spot for, among other things, arguing that there were a multiplicity of planets out there and that there was life out there. And the church, at the Inquisition at that time, did not look kindly on it. That was a heresy. So that's what happens. That's what can happen in the world of belief. But what we have now, and this is really extraordinarily new, is hard-baked science, is real data that's telling us about how there could be life out there and where we might find it and what it might be like. First part of the hard science here is the world of extremophiles. This began some decades ago. On your left here, these are black smokers, hydrothermal vents at the bottom of the Pacific. They go up to something like 600 degrees, not right in the middle, but not too far from the middle. You're going to find microbial life living in settings that, until that time, were considered to be absolutely inhospitable, impossible. The same thing on the right, that's the Taylor Glacier in Antarctica, and it turns out, who could have imagined this, who could have known, that Antarctica is a huge biome, that inside all of these chunks of ice are microbes. There's microbial life. The ice crystal forms, and outside of it is a little rivulet of what's left over, and in that area, the salts, the other nutrients that would be needed for microbial life exist. So you go down into Lake Vostok, which is this huge lake that was found 15, 20 years ago in Antarctica. It's as large as Lake Ontario. No one knew it was there, but people are about to enter it, and the assumption is that there's going to be life there, just as there has been life all the way down. Similarly, this is the Atacama Desert in Chile. It's often used as an analog to Mars. There are places here where it doesn't rain for 8-10 years, and yet there's life underneath some of the rocks, and it again is suggestive of how extreme environments can be, and still biology can occur. One of the extremophile aspects that I really got fascinated by was down in the deep mines, deep gold mines of South Africa. This is Tullis Onstad, who, like many astrobiologists or people involved in astrobiology, posited a theory that everyone said was crazy. He got no funding for it. He said, I think if I go deep down into these mines, I'm going to find microbial life. And everyone said, no, that's absolutely impossible. There's no relation to the sun. How could they, what would they use to eat, and what kind of pressure would they live under, and whatever. So he went down. And among the things that he found over time was this microbe, which is perhaps one of the most famous microbes now on Earth. It has been down there at least 4 million and as much as 40 million years without any contact with the sun, with the Earth. It's about 2-3 miles down, and its energy source is the radioactive decay of some of the rocks nearby, the thorium and I think uranium. And the whole idea that you could have microbial life without any connection to the sun was kind of revolutionary. People thought maybe there could be, but to actually find it was a real breakthrough. Why are microbes a big deal? Well, there's been life on Earth maybe 3.6, 3.7, 3.8 billion years. Almost all of that was just microbes. It was just single-cell microbes. And then, evolution begins or takes off, and suddenly there are cats and us. And that's what we can imagine on other planets. If there is a hospitable kind of environment, then microbial life over time, if it isn't if there isn't some kind of extinction event, why wouldn't it evolve? It did here. Being a foreign correspondent at heart, I of course had to go down into the mines. This was 1.2 miles down. This is in northern South Africa, a platinum mine. It was really, really hot. You know, the deeper you go, the hotter it gets. And it was kind of wet because there were boreholes that were open, and it was extremely hellish. But it was absolutely fascinating because, you know, all you see are rocks. And based on what Tullis Onstadt and others have found, you now know that there's actually life in the cracks, in some ponds and whatever else within the rocks. This is a gentleman I went down with. His name is Gaetan Bourgani. He's from Belgium. He's a nematodologist, little roundworms. He thought, you know, roundworms could live anywhere. You know, if there's microbes down there, then why wouldn't there be roundworms? So over a 3-year period, he also, on his own sabbatical, on his own money, went down to South Africa, met up with Tullis, went looking for these things, and about a half a year ago in Nature published a piece about this worm, worms from hell, and this really took the whole debate or the whole issue a step further, because now you had not only microbial life, but you had complex life at depth, and we don't really know what all that says yet, and how and the meaning of it, but we now know that it's true. Okay, the place where this has the most meaning in the near term is Mars, which we now know as cold and dry. You know, you've seen the pictures of it. It always looks kind of like an extremely dry desert. But this is a NASA image put together saying that in a period of 4 billion years ago or so, Mars was believed to be much wetter and much warmer. It had an atmosphere, it had a magnetic field. It had a lot of the conditions that potentially could have been positive for life. And so the logic is, if there was life there, did it eventually come here via asteroid, which would make us Martians, of course, but also the whole notion of extremophiles and that there's life deep down below. As conditions got worse, they might have just gone down. But also, things happen on the surface. This is a recent set of images from a crater on Mars. Okay, you see here, not a whole lot happening. See those brown-black rivulets? It's postulated that is briny water right at the surface or very near the surface. It hasn't been confirmed yet, but this was found on a number of different places, and it is very suggestive of the fact that when that area heated up, ice melts, it drains down. It obviously had to be kind of briny because it's still not all that warm. You need the salt to make it freeze, to warm up more quickly. And there you have it. I mean, water is what it's all about. Also, recent work at NASA has found that methane, which is 90% of the methane on Earth is created through biology. There are other means to create it, but most of it is through biology. Methane had been found in very trace amounts in the Martian atmosphere in the past. What Mike Muma and his team did was they found, in fact, that there are very large releases of methane at particular places and at particular times. And again, suggestive of a reservoir of methane deep down or somewhere accessible, and that when that area warms up, the ice breaks and the methane comes out. It could be pools of old methane from, created through geological processes. It could be methane that came from things that lived long ago. or it could be methane coming from methanogens that are alive right now. We're going to learn a lot more about this. This is your tax money at work. Curiosity and the Mars Science Lander are headed for the moon. I mean, for Mars, hopefully they're going to be taking off the day after Thanksgiving or soon after. This is by far the most sophisticated rover that's ever gone to the moon. To Mars, I'm sorry. And hopefully it will find, if not life, it's not intended to find life, but it's looking for the components of life, organics and habitability. Okay, another aspect of the whole picture of astrobiology is that we now know that all of the elements needed for life, the water, the complex hydrocarbons, amino acids, oxygen, everything, it's all out there. It's been detected. Whoops. And we also know that the cosmic dust that contains these things is raining down on us all the time, and that back in the times of the early late bombardment, which was about 4 billion years ago, that the amount of material, hydrocarbons and others, that were coming down from space was enormous. So I went to the Murchison meteorite, which is down here on the Mall, the most studied meteorite on Earth. It fell in Australia in the late 60s. They have discovered approximately 80 amino acids in the meteorite now. Amino acids are not life, but they're a building block of life, an essential building block for making proteins. And some of them are not found on Earth, so we know that it's not contamination. So a lot of important material can come down from the skies. And the question is, did the building blocks of life come from afar, or were they generated here? And it's looking more and more like they came from afar. Okay, Paul will go a lot more into this, but another leg of the stool is exoplanets, which really changed the whole discussion. It was only 15, 16 years ago that no exoplanets had ever been detected. They had been speculated. They had been assumed to be there. But it wasn't until first a Swiss team, but then a much better team involving Paul, identified the first one, and subsequently many, many more have been found. This is a recent paper by Jeff Marcy and others suggesting that based on the planets that have been detected so far are mostly large planets, because that's what we had the technology to do, although Paul will tell you that that's changing. But just based on what we found, he posits that there's every reason to believe that there are a lot more smaller planets than there are larger planets. And smaller planets means more likely to be terrestrial planets. And terrestrial planets means more likely to potentially have an ability to hold water. This is an image from a talk or a presentation by Paul and his colleague Steve Voigt about a year ago now, when this was the first planet described to the public as being potentially in a habitable zone. A habitable zone is one where there can be liquid water. It's not too far away from the sun that it's all frozen, or not too close that it all evaporates. This is, like much of science, this is still in process, and there's debate back and forth, but suffice it to say that there's every reason to believe that habitable planets are common. Just like what Jeff Marcy and others have concluded is that the number of habitable planets in the Milky Way alone, which is just one of hundreds of billions of galaxies, that there are billions of exoplanets in the Milky Way. All right, just to step back for a sec, a lot of stars out there. When I started 3 years ago, I believed that there was a 2 there instead of a 3. So there's an understanding of what we're dealing with in terms of of the vastness is something that is growing all the time. So here's the logic of extraterrestrial life. Why I'm a journalist, I'm not a scientist, but this is why scientists, why there's a consensus that there is going to be extraterrestrial life out there, and that in the not too distant future, we'll probably find it. Life is more tenacious than previously imagined. Many billions of exoplanets likely to exist. Habitable zone planets probably common. The molecules and compounds needed for life are out there. Once life has started, why wouldn't it again? And this is, to me, what is so fascinating that kind of pulls it all together. If there's just a microbe found on Mars, or microbial life on Mars, or the possibility that there was sometime in the past, and that it's a different kind of life than what we have here, then when you think about it, we will have had two genesises in one solar system, which is kind of a chump change solar system. It's not that different than most others. If it's the case that life started twice in one solar system, then the probability that there's a lot of life out there goes up like this. It would be impossible from a probabilistic point of view for that to be a singular kind of event. Okay, what are we looking for? Well, obviously we're not going to find ET. That's what we'd all like to see, but it's not going to happen. These are called snotties. They are, for obvious reasons, they are microbial mats. It's a possibility. This is a nematode. Who knows? Maybe it's a possibility. But here's the problem. Alpha Centauri is the closest star, 4.2 light years away. How are we going to ever get there, to find out what's there in terms of the actual kind of life? We could detect different aspects of, or understand that there is life, but to find out what kind of life there is and whether or not maybe it's intelligent life. So that's where SETI comes in, which most of you probably know about. It's a fascinating thing. It's an effort to try to listen for signals put out by intelligent extraterrestrial life, and also there's an effort now to do that in terms of lasers as well, to find the light that comes down. It is. They've been looking to one extent or another for 50 years. Some people say, well, they found nothing. It's kind of over. I was speaking with Jill Tarter, who's the head of SETI and who was the person in Contact, who was played by Jodie Foster. And she says, well, what we've looked at so far is equivalent to 1 cup of water out of the ocean. And so to write it off as being, well, we haven't found anything yet is really kind of not meaningful from her. And I also spent some time in Japan where there was an all-Japan SETI observation. This is just a way of saying that this is a subject and a set of technologies that is of huge interest around the world. This gentleman later organized a worldwide SETI that ran last year. Who knows where it's going to go, but here's my basic point about it, that it is, unlike all the other things that I've just described, this is using science, but it's still kind of in the world of belief, back where Giordano Bruno was. I don't know how to go back. And hopefully someday we will be able to reach that, but as of now, we have a really strong body of science that says that there's a very good chance that there's extraterrestrial life, that there's a canvas out there that all of these elements can come to, and it makes sense that they would be there. And then now the next issue would be, is there intelligent life? And that's kind of beyond the horizon at this point. And at that, I will end it and introduce Paul Butler, who I had the great privilege of meeting down in, is from your website, Paul. You can't blame me. Meeting down in Australia, where he spends a great deal of his time working at the Anglo-Australian Observatory telescope. He as has been said, has been involved with the discovery of maybe half of the exoplanets that have been found. And some of them have been done here at this observatory, which was commissioned by Prince Charles when he was like a teenager, right, or in his 20s. So it was kind of a long time ago. And the technology here is not the greatest, but for Paul it's perfect because other people aren't coming there and demanding time, and he needs to watch things over and over and over again, and so he spends a lot of time there. It's a place called Coonabarabran in the shadow of the Warrumbungle. When I told my wife I was going there, she said, "Yeah, right, you're going to Coonabarabran in the shadow of the Warrumbungle." But I really did. And Paul is kind of the master of planet hunting via Doppler resonancing. He will tell you all about it, but he has not only been involved in inventing the process, but also in expanding it and making it so that it can do things that are just utterly remarkable. He loves everything. He loves things Australian. He's married to a wonderful Australian woman, but he hates kangaroos. I didn't know how serious to take this. He calls them rats with tails. He said, when we walk at night back from the observatory to the places where we stayed, he said, you got to watch out, they can attack. I was like really scared. It's 3 o'clock in the morning. As it turns out, they are a danger because they tend to jump on cars, which is a problem. But I don't know. They still seem kind of nice to me. So, a magnificent scientist, a wonderful person, although a hater of kangaroos, Paul Butler.
It is a great pleasure to be here today, and it's great to see Mark again. You can tell that Mark is not a true Australiophile because he does not hate kangaroos. Anybody who spent any significant time down there absolutely despises these giant-tailed rats. Looking for planets. The most obvious way to look for a planet is to point your telescope at a star and try to see that teeny faint little planet right next to it. And in fact, people have been trying to do this for about the last 402 years, a telescope being invented 402 years ago. So far it has not been successful, and the reason is because planets only shine by reflected light. So even a giant planet like Jupiter is only about 1/1 as bright as the sun. So if you're trying to look for a planet, you've got something that's 1 billion times fainter than the star right next to the star. Absolutely impossible to try to find. So the technique that people are pursuing are so-called indirect techniques where you look for the influence that the planet has on the star. Here's a nifty animation that shows what's going on here. We normally think of a planet orbiting a star, but in this case you can see the planet and the star both orbit the common center of mass. This is literally, if you imagine the star and the planet is like a fat kid and a skinny kid, and they're on a teeter-totter, the common center of mass is the point where you'd put the fulcrum on the teeter-totter such that the two would balance out. So what we're actually looking for is seeing a star wobble in space, periodically wobble. One way to do this, the way that people have been trying for the last 100 years, is to take photographs of a particular star field. And you photograph that same field week after week, month after month, year after year, and you look for stars that are wobbling relative to the more distant background stars. This is called astrometry, and people continue to work on it, including astronomers at the Carnegie Institution. but as of yet, it has not really panned out. The other way that you have a chance to detect the motion of the star is the so-called Doppler wobble, so that as the unseen planet orbits the star, for half of the orbit, the star is approaching the observer on Earth, and the light from the star will be Doppler shifted to slightly shorter wavelengths. For the other half of the orbit, the star is receding from observers on the Earth, and the light gets stretched to slightly longer wavelengths, the so-called redshift and blue shift. This is, in principle, the same as a highway patrol officer using a Doppler radar gun to catch speeders. So in this case, you can see that Doppler spectroscopy can be used for both good and for evil. Okay, so with this technique, imagine we're alien astronomers. Imagine we're on Alpha Centauri or some other star, and we're looking back to the solar system. What would this technique say about the solar system? If we could make very precise Doppler measurements of the sun over, in this case, over a 60-year period, you would see that you get this periodic shift with the sun's velocity going positive 10 meters a second and then negative 10 meters a second, and that the period of this is 12 years. That's Jupiter. And in fact, Jupiter is the dominant planet in the solar system. To first order, you can describe the solar system as consisting of the sun and Jupiter and some garbage. If you could make even more precise measurements over a much longer period of time, you'll notice that the peaks from 12-year period to 12-year period go up, down, up, down. That's due to Saturn. Saturn is the next biggest planet in the solar system. And with the techniques that we have today, they're the two planets that we could hope to detect. So, like as in the case of Mark, I like to step back just for a second. I know sometimes people get confused about galaxies and constellations and so on. This is one of these "You Are Here" photographs. If we could imagine that we could step outside of our own galaxy, the Milky Way, this is what it would more or less look like, a beautiful spiral galaxy. And that little pink dot in the center, that's supposed to be the "You Are Here" part. That's more or less where the sun would be. So you can see we're not in the downtown of the galaxy at all. We're way out in the exoburbs. We're not where anything terribly interesting is happening. And I've drawn a couple of circles here indicating different distances. But in fact, for Doppler spectroscopy, the technique that's found virtually all the nearby planets, that little pink dot, which is about 50 parsecs, about 150 light years, that represents the entire volume that we've searched. So you can see what a teeny fraction of the galaxy we've been through. And as Mark pointed out, our galaxy has something in the ballpark of 200 to 400 billion stars, and there is something like 200 to 400 billion comparable sized galaxies that we know of in the universe. So, what really excites us about extrasolar planets? It's the much bigger question. Are we alone? Is there something else out there that we can communicate with, or is there just anything out there at all that's alive? And one of the very first people to try to seriously quantify this is Frank Drake, who I've had the great pleasure to meet on a number of occasions, usually in the back of a taxi cab in some foreign city heading to an airport. And Frank literally invented SETI in 1960, year I was born, and pointed a very early radio telescope at two very near sun-like stars in hopes that he would pick up their equivalent of "I Love Lucy" on the radio. And we've seen from Mark that this has now been tremendously expanded over the last 50 years, and yet the search still is a very teeny part of parameter space. When Frank started, he needed some unifying way to describe what he was trying to do. And so the big question is, how many communicating civilizations are there in the galaxy? So the SETI project is looking not just for life, they're looking for intelligent life. And the SETI definition of intelligent life isn't just like, it's not just like having Shakespeare's or Michelangelo's making beautiful art. That doesn't count. What counts in the SETI sense of being intelligent is that you can build a radio telescope big enough to communicate between the stars. And by that definition, humanity became intelligent only about 100 years ago. So we're newbies. When Frank started this, he's trying to answer how many communicating civilizations are there in the galaxy. And so he parameterizes this with a number of smaller steps, starting with how many stars are there in the galaxy, what fraction of those stars have planets, and so on. You can read the list. The thing that's remarkable is that prior to 15 years ago, the only thing on that list for which we had any information was how many stars there are in the galaxy. Other than that, every last thing up there was a complete and total guess. And with the discovery of extrasolar planets over the last 15 years, we now can put serious constraints on the fraction of stars that have planets. And as you'll see in a few minutes, we're beginning to move on to the next step, the fraction of systems that might have Earth-like or potentially habitable planets. I started in this business about 25 years ago, and at that time, looking for extrasolar planets was not something you would say in polite company. In a group of astronomers, if you admitted you were looking for planets, you might as well say that you're looking for little green men. People would kind of snicker and move away from you like you smell bad. On the other hand, that's still much preferable than the reception that Bruno got. So I guess I shouldn't complain too much. When planets were finally discovered in 95, in October of 1995, in fact, 11 years ago, 12 years ago, it was such huge news that the discovery of the first couple of planets led to the cover of Time magazine. And for a year or so, every time we discovered a new planet, there'd be huge newspaper stories, which was really bizarre, having spent the previous 8 years mostly hiding in a dungeon writing computer code, trying to tease the signal out while people basically thought I was an idiot. The really bizarre thing that emerged from these first few planets was that everything we knew was wrong. Prior to the discovery of planets, everybody knew, and by everybody I mean the smartest astrophysicists in the world, the science fiction producers, and everybody in between knew that all planetary systems would look just like our own, that you'd have giant planets further out, small rocky planets like the Earth closer in, all of them orbiting in beautiful circular concentric orbits. So this is the first planet that emerged, 51 Peg, around a sun-like star. And the immediate thing that you notice is that the period from peak to peak is about 4 days. There's no 4-day planets in our solar system. And furthermore, the thing is about a half a Jupiter mass. So it's of order of Jupiter mass, a giant planet orbiting 4 days from its star. Literally inconceivable. Nobody had ever thought such an idea. Truly amazing. One of the cool things about these so-called hot Jupiter systems is that you can put a scale model of the entire thing on a piece of paper. Sun-like star, the planet's about 1/10 the diameter of the star, and it's about 10 stellar radii from the star. So the whole thing fits like this. Try to make a model of the solar system, and you put the sun here, Jupiter ends up being in West Virginia, so that doesn't work. One of the next earliest planets that was discovered is 16 Cygni b. Turns out that of the 9,000 stars in the Bright Star catalog, this is the star that is most identical to the sun. You take a spectrum of the star and it literally lays line for line directly on the sun, just a remarkable solar analog. And it has planets like the sun, but the bizarre thing is here, the shape of this planetary orbit. It's like a sawtooth. It's not like the smooth sinusoids that we've been seeing up until now. The period's a little bit more than 2 years. The masses of order 2 Jupiter masses, but this bizarre shape is telling us that this orbit is not circular. And in fact, if you were to look at how this orbit actually is overlaid on the solar system, here's the solar system, Mercury, Venus, Earth, Mars, all in nice, beautiful circular orbits. And here's what the 16 Cygni b planet would look like. Swings inside the orbit of Venus, swings way out beyond Mars. Again, nobody had thought that there were going to be eccentric planets. Everybody knew that all planetary orbits were circular. And initially people thought, okay, this is a wacky thing, it's a 1 in a million, so you can sweep it under the rug. It turns out this is the most common configuration for planetary systems. Most planets orbit in eccentric orbits. Circular orbits like our own are relatively rare. For the first 15 years or so of the extrasolar planet revolution, our measurement errors were about 3 meters a second. Jupiter, for instance, kicks the sun by about 10 meters a second. And when I got started in this business, it was not possible to make a measurement more precise than about 300 meters a second. But with 3 meters a second, we could detect Jupiter-like planets, but we were really stuck. And if we wanted to move on, we had to get much higher precision. And by pushing our precision to 1 meter a second, we're in a position where we can begin to try to detect terrestrial mass planets and potentially habitable planets. So this is looking for planets with the Doppler technique. It's really very simple. It's like being in a race car team. If you're in a race car team, you want to make your car go faster, and you want to make it handle better in turns. That's basically it. In the precision Doppler game, you want to do two things if you want to make more precise measurements and find smaller mass planets. You want higher measurement precision, and you want lots and lots and lots of nights on the telescope, so-called high cadence observing. Here's an example of what you get from high cadence observing. This is a 48-night data set from the Anglo-Australian telescope that Mark just described. And you can see that there is this periodicity of about 4 days. That's a 5 Earth mass planet. That's something that we can now compare to the Earth. And then there's this longer period planet that's got a period of a couple of months. And you really need this high cadence data set to tease out this signal. Life would be much easier if stars had one planet. You'd get your nice repeating signal, and you wouldn't need to observe it every single night. But nature is basically malicious and likes to make things really very difficult. And often we'll throw in 2 or 3 planets, and the only way to pull these signals out at this level is to get this very high cadence observing. So one of our 2 struggles is to get lots and lots of telescope time. Here's what that wacky system looks like, so-called 61 Ver. It's got that little 5 Earth mass planet in the 4-day orbit, and then this planet that's got a couple of months period. It's about a Neptune mass, about 15 Earth masses. And then it turns out there's a 3rd planet in this system with a longer period that's about 2 Neptune masses with a period of about 3 or 4 months. The observations for this 61 Ver system came from Keck, the world's biggest telescope, on the hopefully extinct volcano of Mauna Kea, and from the Anglo-Australian telescope. They don't have particularly good security at the Anglo-Australian telescope, and so all sorts of riffraff are able to sneak in there. But far worse than journalists are these long-tailed, giant-tailed rats. I had been telling Mark, any Australian will tell you how much they hate ruse. Any Australian who lives in the country has hit ruse on more than one occasion. And I had been going through telling Mark all these horror stories about ruse. And at the end of this observing run, it was just raining cats and dogs. And I left in the middle of the night because there was no hope of opening. And I got about 2 miles down the mountain when I hit a roo. They are unbelievably tough. I hit it at about 25 miles an hour. I threw it in an arc of about 50 feet. It landed like with a splat in the middle of a rainstorm. You're supposed to get out of your car and bash its brains in to put it out of its misery. But it was really raining hard, and I thought, this ruse on its own. And started the car back up, was going about 2 miles an hour when the roo jumped back up and then jumped right back into the car. The project I'm most excited about right now is the Magellan Planet Finding Spectrometer at the Carnegie Observatory in Las Campanas. The gorgeous sunsets. It's actually the bane of astronomers to have a gorgeous sunset. And what we've done here to push to much higher measurement precision is we've built an all-new spectrograph, and this is largely done by our sister department, the Carnegie Observatories in Pasadena, California. The spectrometer was originally designed by Steve Scheckman, and it was the design was further refined, and most of the construction was carried out by Jeff Crane, and Ian Thompson built the CCD detector at the heart of this thing. I won't go into this too much, but this new generation of spectrometers has, because it's custom built to do nothing but make precision velocity measurements, has a number of fabulous built-in features. It's extremely high resolution. It's in a constant gravity environment. It's athermalized. In fact, in the case of the planet finding spectrometer, that big box is 2-inch thick styrofoam with heating elements on the inside, and the temperature of the box is maintained to plus or minus 1/100th of a degree centigrade. These are extremely efficient. We get about 35% of the light that enters this thing we actually end up detecting. In comparison with the older generation spectrometers, we would have efficiencies of about 5 or 10%. So we literally are getting a gain of like about 5 to 7 times in throughput. It's like doubling the size of our telescope. High resolution, and the goal here is to get to 1 meter a second. And the cost is moderate for these things, about $2 million. This is actually the Carnegie Observatory's optical lab. The spectrometer is just off screen right here, and here's Jeff Crane, and here's Steve Scheckman. There was a big celebration for Steve Scheckman because he's truly one of the great giants in the field. And I like showing this photograph because we needed to get light into the spectrograph for testing. So he pulls off this mirror and he's just reflecting light from the window into the spectrometer. So this is a case of a person who is so deeply into his job that he literally has become one with the instrument. And here are some, here's a recent result. In fact, this is data that I took about 2 weeks ago before I got stuck in Chile thanks to the volcano. This is data that we've been taking over about the last 6 months. And as you can see, we've been moving towards higher cadence. We were trying to hit these things now every night that we can. And here you see 2 signals, a rising signal suggesting a long-term planet, and then this thing with a 19-day period. The amplitude is now only about 3.5 meters a second. The scatter of the model fit to our velocities is now down to 1 meter a second. The mass of this 19-day thing is about 8 or 9 Earth masses. So an 8 or 9 Earth mass object, sometimes they're called super-Earths, if it's made out of basically the same stuff the Earth is made out of, it'll be about 2 Earth radii, being 8 or 9 times the mass of the Earth. It'll have 8 or 9 times as much mass for gravity, but on the surface, you're twice as far out, so the gravity goes as inverse square, so your actual surface gravity would be about twice that of Earth. So if you could have liquid water on such an object, single-cell creatures don't care that they're in twice as much gravity. They would be quite happy to live. These things could be quite habitable, and we're basically just itching to get more data on this system. The other system that is about to really change the game for us is the Automated Planet Finding Telescope, a 2.4-meter telescope at Lick Observatory in Northern California. And this telescope and spectrometer are custom designed to do nothing but find extrasolar planets. My collaborator Steve Vogt at UC Santa Cruz has been the lead on this, and we hope that this will actually go into full science production in about 3 weeks. I'll be spending a week there in the middle of November. And we'll be getting 180 nights a year on this telescope. And we'll pick 20 or 30 stars that are really exciting and hit them every single night for months on end. And that's the sort of commitment you need in order to find Earth-mass planets and potentially habitable planets. So I'd just like to end by pointing out that this is a big collaboration. And many, many people have put literally their entire lifetimes into this. And for me, it's been a real pleasure to work with these people over the many years. So I'll end there, and thank you very much.
with a couple of questions to Paul. As he knows, I spent a whole week posing questions to him, and I love doing that, so I'm going to just continue it a little bit, and then we'll open up the floor for questions from you folks. And the first question that comes to my mind, something seems to be coming between us here, that there's been a lot of reporting about planets, exoplanets, that have been discovered by Kepler at a very far distance. Maybe you could explain to us what the difference is between the 1,000 or so candidate planets found by Kepler and the roughly 600 or so that we're discussing right now.
Kepler is a very nifty mission that NASA launched a couple of years ago after literally 20 years of preparation. And the goal of Kepler is to very quickly learn what fraction of planets or stars have Earth-mass planets. And what Kepler does is it's basically just a camera with a giant field, and it photographs a single field in space over and over again. It takes a frame every 30 seconds or every minute, and literally just simply photographs 100,000 stars just repeatedly. And it looks for planets with the so-called transit technique, which I didn't get into here. But in the transit technique, you can find a planet if you're lucky enough that the orbit of the planet takes it across the face of the star as seen from Earth. So in the case of Jupiter, if a Jupiter-like planet crosses the face of a Sun-like star, Jupiter is about 1% the surface area of the Sun, it'll block about 1% of the light. And you can see a little notch literally in the brightness of the star while the planet is transiting the star. In the case of an Earth-like planet crossing the face of a star, you've got a much bigger problem. Earth is truly teeny in comparison to Jupiter. Jupiter is about 300 Earth masses, and the amount by which an Earth will dim a star is about a part in 10,000. Can't make that measurement from the ground. The atmosphere, the scintillation of the atmosphere makes that impossible. So you have to put your spacecraft, you have to put your mission in space. So that's what Kepler did. And Kepler, like I say, is monitoring about 100,000 stars. It has to monitor that many stars because it can only detect those systems in which you're lucky enough that the orbit of the planet goes directly in front of the face of the star. So if you have nice giant planets like Jupiter and short orbits, 3 or 4 days, it's easy to make these detections, and they've made many, many of these detections. The problem is, of course, that in order to get 100,000 stars in your field, the stars have to be systematically much further away. We're looking at stars that are a few tens of light years or even closer. They're looking at stars that are 1,000 light years or 2,000 light years away in order to get enough stars in the field of view. So at that distance, the stars are now much fainter. Our technique, the Doppler technique, still works, but it's much harder because you don't get as much light from the star. So in the case of giant Jupiter-like planets transiting, you can do the Doppler technique and you can confirm the existence of the planet, and that's great. And that's actually been done now for many tens of these. For the smaller planets, which is the whole point of Kepler, to find Earth-like planets, the Earth does not tug on the Sun strong enough to be detected with current generations of precision Doppler techniques. The Earth causes the Sun to wobble around by about 10 centimeters a second, about a factor of 10 smaller than our current measurement error. So what you can do with the Doppler technique is you can follow up the star and see that you don't see a signal, which is bizarrely what you want to see in that case, because that at least suggests that there might really be an Earth there. But you're not really sure. So you can do simulations and you can say, I think there's a 90% chance that that's an Earth-like planet. And if you have an ensemble of hundreds of these, then you'll know that about 90% of them are right, but you won't know which 90% are right and which 10% are wrong. So that's where we're at with Kepler. And in the next 3 or 4 years, as the Kepler mission winds down, we'll have an answer. We'll know what fraction of Sun-like stars have Earth-like planets, and that's really the goal of Kepler. It's a short circuit to that answer. What we're trying to do by focusing on the nearest stars is to actually come up with candidates for next generation missions that will actually be able to begin to take images of the planets and then ultimately follow up and begin to take spectra of the planets and then hopefully get to the question of life.
And speaking of life, I mean, the fact that you have now, or you and others have found that eccentric orbits are the norm, what, if anything, does that imply in terms of habitability? It seems like a planet that's going eccentrically would be less likely to be habitable.
Right. A planet in an eccentric orbit is going to have a large part of its orbit closest to its star. It might be quite hot, and then another fraction of its orbit quite far from the star, and it's going to be incredibly cold. So if you believe that liquid water is the key to life, you could conceivably go in a situation where you go from literally boiling oceans to freezing oceans. And so one might imagine that that would be not a great environment for life. I personally, though, I'm an astronomer. I'm not a biologist, and I feel really silly commenting on the possibility of life in these things, as we found, you know, from your own book, that life exists in all sorts of bizarre places on Earth that nobody had ever imagined before.
Okay, and a last question from me. There have been these estimates of tens of billions of exoplanets in the Milky Way alone, and maybe a billion habitable zone planets. Is there any reason to think, from the work you've done, that that's accurate?
Planets are absolutely ubiquitous. Almost every star has planets. There are absolutely hundreds of billions of planets in the Milky Way galaxy. Earth-like planets must be very, very common, even if they're rare, even if there's only one per every 1,000 stars. That still puts you at millions and millions of planets. So planets are everywhere.
This is, to me, what's kind of so remarkable and so revolutionary, that what Paul just said, that planets are ubiquitous, and that that there's every reason to believe that they're going to be in habitable zones. This is stuff that 15 years ago, 10 years ago, nobody could say, and it's a huge revolution in thought. So we'll open up to questions here. There are two microphones, and we're happy to take any questions about anything, since astrobiology is about everything.
Without getting into the Pluto debate, I'm just curious, do you think that the International Astrophysical Union is going to have to redefine what a planet is? Because we based it strictly on our solar system. Now that we've got all these new planets out there, should there be some corollaries in there depending on where the planet is in relation to us?
The IAU actually has a working committee on extrasolar planets. It's a very bureaucratic organization, and it loves stuff like this. So if there's any astro lawyers out there, there's a future for you in this business. In the case of extrasolar planets, in the case of the solar system, the issue for Pluto was it was too damn small. Okay, that's ultimately why it got booted off of the island. In the case of extrasolar planets, we would love to be able to find things so small that there was a question of whether it's a planet or not. But we're not there yet, okay? So we don't need to worry about the low mass end of things. The high mass end of things is interesting, though. When is an object a planet, and when is it too big to be a planet? And there has been a line drawn in the sand, roughly 13 Jupiter masses. If an object is less than 13 Jupiter masses, okay, it's a planet. Oddball, but a planet. If it's more than 13 Jupiter masses, then it's a so-called brown dwarf or a failed star. And one of the reasons that the line has been drawn at 13 Jupiter masses is because of physics. For things that are less than 13 Jupiter masses, there is no nuclear processing. What you see is what you get. For things that are more than 13 Jupiter masses, there's enough gravity in the core of the object to begin deuterium fusion. And you get a little bit of nuclear processing, not for very long, but you do get some nuclear processing, so people now use that as the dividing line.
Hi, you showed briefly on a slide, but didn't actually discuss much, the different things that are limiting the precision now. In your latest and greatest spectrometer, the APF, is that what you call it? What is it that's now keeping you from getting even better? than, say, 1 meter per second?
Well, I didn't get into how really difficult these measurements are. You know, in the old days, the detector at the back end of a spectrograph was a photographic plate. Okay, photographic plates are now gone, and we now have these fancy CCD detectors, the same thing in the back of your iPhone or your pocket camera. The individual pixels on these CCDs are 15 microns. I don't know what fraction of a human hair that is, but it's a very small fraction. We are measuring at 1 meter a second, we're measuring shifts that are less than 1/1000th of a pixel, that are about 20 silicon atoms on the CCD substrate. So to get down to this level of precision really is a remarkable struggle against nature. Nature is a vicious, malicious beast. But it gets worse. That's simply at the technical level. The ultimate floor of the precision that we'll ever achieve is due to the stars themselves. I would prefer that stars were billiard balls, nice, solid, hard objects for which the surface itself does not ever move. In fact, stars are these giant roiling, broiling gas balls where you've got drafts of hot air and down drafts of cool air. The stars themselves rotate and have spots. These spots can give you pseudo-Doppler signals. Back in 20 years ago, people thought that maybe the stars themselves would prevent you from making measurements even at the 10 meter a second level. Well, we now know that at least for the quiet stars, you can get down to 1 meter a second, but we know that the floor cannot be far away. Now that we've gotten to 1 meter, I imagine a pathway to get to a half a meter. If and when we get to a half a meter, then I'll start talking to you about how we get to a tenth of a meter. But we are going to ultimately be hit by the stars themselves.
Yes, I've been reading that our planet is in a perfect zone. They call it the Goldilocks zone or something. I'm not exactly sure what that is, but are we finding other planets in this perfect zone or for life out of the 600 or so?
Yeah, Goldilocks, means not too close, not too far. And in particular, it means with respect to liquid water. That's the one key thing that all the biologists seem to maintain is you have to have liquid water to have life. There are, right now, finding planets in the habitable zone is the holy grail. That's what people really want to do. And the discoveries are now trickling in 1 or 2 at a time. And they're getting a lot of publicity as they come in. Like they might get 5 seconds on the evening news, and they might get a mention in the newspaper. But I think that this is about to turn into a flood, and that within the next 5 years, there will be many, many planets that are known in the habitable zone, particularly around the smaller mass, so-called red dwarfs or M-dwarf stars.
Just an addendum to that. We tend to think of these habitable zones as in, the area around Earth or between Venus and Mars, somewhere. But some of the celestial bodies that are believed to be most likely to have life in our solar system are Europa, which is a moon of Jupiter, Enceladus, Saturn, and so Titan. So it's kind of it's a somewhat fungible thing. I mean, we're talking about the light of the star, but we're also talking about tidal heat, or heat coming from tidal movement or radioactive kind of thing. So it's a complicated scenario.
I have a question about the Alpha Centauri system, which was mentioned on one of the slides. I know that it's not definitively known whether or not there could be planets there, but I was curious to what extent have previous searches ruled out planets of certain sizes or certain orbital distances from the stars, and what techniques and plans are there currently to continue searching Alpha Centauri and other nearby star systems?
The nearest stars are by far and away the most interesting. They're the stars for which in the next generation, in 10 or 20 or 30 years, people are going to figure out how to begin directly imaging the planets and how to detect them astrometrically. And then once you can directly detect a planet, then you can start taking spectra of the planet and looking for things like water vapor or oxygen in the atmosphere. So Alpha Cent is a wonderful entry to that because it's the nearest system. Alpha Cent A and Alpha Cent B are 2 sun-like stars. They orbit each other with a period of about 100 years. And being that they're alpha Cen, it's kind of the law. If you're doing a planet search and you can reach them, you kind of have to do them. And so we have. We can rule out from our own data that these have Jupiter-mass planets around them. We would have detected them by now. It was already thought that they probably wouldn't have Jupiter-mass planets because of the gravitational interaction of the companion star would make these orbits difficult to find a stable zone. Smaller mass planets in much closer to one star or the other, Earth mass planets that are, maybe at an Earth orbital distance or closer, those might be gravitationally stable. And people are definitely pounding away trying to detect these sorts of planets. It turns out for direct imaging, the most important thing is how close the star is to us. As you get more distant, the angular separation of the planet and the star diminishes and it becomes impossible to detect. So alpha Cen will remain sort of a holy grail for the rest of this century.
What is the main focus of current research regarding exoplanets? I mean, is it either on the side of finding more exoplanets in solar systems in order to increase the probability of finding habitable zones, or is it more on the side of finding more Earth-like planets within the planets that we already found?
Yeah, I'd say that the holy grail right now, and you get flavor of the month. Some part of research becomes very hot for a year or two, and then it goes away. But right now, the very hottest thing is to find potentially habitable planets, things that are less than 10 Earth masses that orbit at the right distance from their star to have liquid water. And I think we're right on the verge of a flood of these discoveries being made. In 5 years from now, these things will be boring. For me, another question, which is a longer-term question, but for me just as exciting, is what fraction of planetary systems have a similar architecture to our own solar system? What fraction of systems have their planets all in circular orbits with small rocky planets in close and gas giants like Jupiter further out? George Wetherill, a former director of my department, the Department of Terrestrial Magnetism, was one of the first to speculate in the 1990s that the presence of Jupiter might have been crucial to us. And early on in the history of the solar system, there was this period of heavy bombardment that Mark talked about that ended about 1 billion years after the creation of the solar system. And at that time, giant objects, things even the size of Mars, were crashing into Earth regularly, and things like the impact that knocked out the dinosaurs, those things were happening weekly and monthly. And it would be very hard to have a nice civilization with electric power if every couple of weeks you were getting hit by a 5-mile rock. So George pointed out that what ended this period of heavy bombardment was Jupiter. Jupiter is basically a giant gravitational bouncer. It's more than twice as massive as all the other planets combined. And now twice in the last 20 years, we have observed comets smashing into Jupiter. And it's not a mistake. Jupiter's gravity first altered the orbit of the comet and then gravitationally acted like a vacuum cleaner to sweep it into itself. And Jupiter is what cleared out all the debris of the early solar system and provided us this nice quiescent place where life could get a toehold and evolve into interesting things like cats. So for me, it remains a huge question. Are there other systems that remind us of the solar system with circular planets and the gas giants further out?
To me, just wonderful, wonderful science, and just allows your imagination to run wild.
Yes, I have a two-part question. One, in terms of the eccentric orbits that are so common outside of our solar system, can the planets that are revolving around these stars, are they affected by each other? And would we in the future be able, through Doppler, to determine the effect of each of these planets on each other in terms of their orbiting cycles, as opposed to in their relation with the star? And secondly, where in time are we, in actual time, looking back and observing these motions compared to our actual Earth time? I can't tell if we're going way far back in the past, or are we in the future? I mean, where are we in time?
Those are two great questions. The first question is about these eccentric systems and whether multiple eccentric planets can gravitationally interact. And the answer is yes, they absolutely can. It's just simple Newton's laws. And in fact, this has already been observed. That as the planets interact, the orbits change. The system can remain stable as long as the orbits don't cross. And the change in the orbital parameters of a number of planetary systems have already been observed. And it's really fascinating. I think Newton would be proud. Newtonian physics continues to work. The second question is look back. Astronomy is, of course, a study of things that happened long ago because we're limited by the speed of light. In our case, we're looking at literally the very nearest stars, things that are 10 light years to 100 light years away. So what we detect is light that left those systems 10 to 100 years ago. So in the astronomical context, that's right now. There's no serious time lag there. It's just a lousy 100 years. For Kepler, it's a slightly bigger time lag, but not much. In that case, it's maybe 1,000 years that we're seeing events. We have here Vera Rubin, maybe the greatest living astronomer, and she studies galaxies where the light that she's collected has left these galaxies literally millions and millions of years ago. And one of the cool things, if you get out of the city into the countryside, is you can see with your naked eyeball the Andromeda Galaxy. That's the most distant thing that the human eye can see. It's about 2 million light years away. So when the light hits your eye, it's been traveling for 2 million years. 2 million years ago, of course, there were no humans. So that's always awe-inspiring for me.
Along similar kinds of lines, as far as we know, the Big Bang occurred, 13.7 billion years ago. I read recently that there was an assessment that there were galaxies, maybe 2-3 billion years after that. So when we think about, is there life in the universe? Was there life in the universe? It's not only a question of, that 3 with 23 zeros after it in terms of the number of stars, but that these things have been going on for maybe 10 billion years, and who knows, maybe there were great civilizations 6 billion years ago, and they died out long before we ever arrived. I mean, millions of years ago before that. I'm being told 2 more questions? 1 more question. 2 more questions. Okay.
Since the closest star, Alpha Centauri, is about 4.2 light years away, how long would it take for us to get a signal to any intelligent life and then have a response sent back to us?
Well, 4.2 light years basically tells you radio signals or optical signals take 4.2 years to get there. So we've been flooding this thing with I Love Lucy reruns now for most of the last century. And sadly, we haven't heard anything back. So by astronomy standards, that's instantaneous, On the other hand, if you take the fastest rocket ship that's ever been built and you do the most clever orbit that's ever been done where you slingshot off of Jupiter and you slingshot off of Saturn, it would take us hundreds of thousands of years to actually get there.
I'm afraid this is the final question, but we will be out by the bookstand afterwards, and we will be happy to answer questions, and I'll be happy to sign any books.
What are our prospects for discovering or detecting large, potentially habitable moons or binary planets in other star systems?
That's an interesting question. So giant planets, like Jupiter, have giant moons. And it's possible that some of the giant planets that have been detected already, while presumably the giant planet is not habitable, that they might have giant moons that are habitable. From the Doppler technique, they're indetectable. All you see is the common center of mass of the moon and the planet. In the transit technique, though, there is a hope. If you were lucky enough that the orbit led the planet directly across the face of the star, then you would see this drop in the light from the star to the planet. But then slightly later, the moon might trail behind it, and then you might see the drop in the light from the moon. So that's one way that you could detect a moon or a multiple planetary system.
Thank you all very much for coming. And it's okay.